I want to quickly run through some important concepts about correlation that are mentioned in your book. First of all, correlation is represented by the letter R. I made a point of this because you are going to later learn about two other R words, regression and residuals. And once students hear the words regression and residuals, they often think R stands for something different than correlation. So remember, R goes with correlation. Correlation measures the strength and direction of the linear relationship between two quantitative variables. Important, all of those things are important, keywords. Correlation is always a number between -1 and +1. If R is positive, it indicates that there is a positive or upward trend association between two variables. If it is negative, then there is a negative association. If R is close to positive or -1, it means this association is very strong, very little scatter in the scatter plot. If it's closer to 0, then it's a weak association. If it's exactly 1 or -1, then it falls exactly on a line. So let's take a look at guessing some correlations and maybe making some correlations. Okay, so here is kind of a moderately strong relationship. What do you think the correlation is? I'm going to guess about 0.5. Not bad, 0.663. I'm a little bit off. Okay, so let's look at another sample. This one looks a little bit stronger. I'm going to guess about 0.7. Okay, I might still a little bit low. It's actually, well, that's pretty close, 0.75. This one looks more like maybe 0.6 to me. Oh, I'm way off on that one. Okay, here's a negative, fairly strong. I'm going to guess this is about -0.85. Not bad. Okay, so it's hard to guess exactly, but let's take a look at this applet right here. I'm going to clear this off. So here are, this would be, notice, a perfect, nice, perfectly strong correlation. Let's put some more scatter in here. So as we add some scatter, notice the correlation is going down. Okay, we're scattering it a little more. We can still see an upward trend, but it's weakening. Okay, scatter a little bit more. Still an upward trend, but weakening. Now, if I keep adding more and more and more points here, notice that we're getting closer to 0, and now actually I have more downward points than I do upward, although it's very hard to tell. If I were to increase the number of points in the downward trend, then it would increase the strength in the downward direction. Okay, so I'm making it stronger in the downward direction now. So just to give you a little idea of what correlation is, if you want to try the Guess the Correlation applet, you can find that on the Chapter 3 notes page. It has the different applets that I'm using in this video. Okay, now I want to look at the equation of correlation. This is not something that you will be required to use and to calculate correlation by hand. We will always be doing correlation using technology. But I want to just talk about a little bit because this illustrates some of the characteristics of correlation. So when you see this, notice it is 1 divided by n minus 1. So 1 divided by 1 less than the number of data points. This is our sprint and long jump example. It had 12 data points, so that would be 11. When you look at these, we're multiplying two numbers together, one for each data value. So xi and yi indicate one particular xy point. So we take one particular xy point, so for example this one right here, we subtract the mean of the x's and divide by the standard deviation of the x's. From the y, we subtract the mean of the y and divide by the standard deviation of the y. This should look familiar because what we're doing is we are finding the z-score of the x value and the z-score of the y value and multiplying them together. So to illustrate that, I took a look at I calculated the z-scores for all of the sprint times and the z-scores for all of the jump times, and I plotted them. So notice right here is 0, 0, so this would be the very center. This would represent the mean of the jump times and the mean of, and we don't have a point there, but the mean of the jump times and the mean of the sprint times. So over in this little section right here, we have values that have a positive z-score in the x direction. In other words, they are higher than the average time. So these are our slower runners. And we have a negative z-score in the y direction, which means they jump less than the average long jump. If we multiply zx times zy, all of these would give me a negative value here, all of those points in that section. In this section of the graph, we have all values where the y z-score is higher than average. So these are the higher long jumpers, and the negative z-scores in the x direction means these are the faster sprinters. They take less time in their sprint. Once again, if I multiply the z-x's times the z-y's, I get negative values. For every point on the scatter plot, I get negative numbers when I multiply these two together, except for this one point right here. I would get a positive value when I multiplied these two z-scores together because they're both positive. So overall, you can see that if I multiply each of these and get negative numbers and add them all together, I'm going to get a negative number for R. So we see an overall negative correlation here. Now you can tell that this is fairly strongly negative, okay, because we see this really strong negative trend. If there were more scatter and some of the points fell in this quadrant or this quadrant, I would end up having some more positive values when I multiply the z-scores together, which would add with the negative values and cause a weaker correlation. So this is kind of how the formula works. Now because these are z-scores, this tells us some things about the data and about the correlation. So let's look at these characteristics of the correlation. First of all, it says correlation makes no distinction between explanatory and response variables. What that means is if I were to switch x and y on the axes, the correlation would not change. So I did a little experiment here. I went ahead and changed my z-scores for the jump and my z-scores for the sprint, and I switched the axes. And then I looked for this same point. This point now is going to, since I switched the x and y's, this point's over here now. Notice that its z-score are exactly the same but switched. Okay, so when I multiply the z-scores together for the x and the y, I'm going to get exactly the same values as I got up here, and that's going to be true for every point. So the z-score, or the correlation, does not change at all when I switch x and y. So you might want to add just one more piece of explanation. Switching x and y values does not change R. Okay, the second one. Correlation does not change when we change the units of measurements for x or y or both. Well, notice here that this would be the original data. The units of measurement would be in seconds and in feet. But if I take the z-scores, now I don't have any units at all. I've changed the scale completely, but look at the scatter plot. The scatter plot looks exactly the same. And since the R value, or the correlation, is based only on z-scores, which have no units at all, changing units doesn't make any difference. Also, correlation has no units because it is based on the z-score. Okay, so correlation does not change when we change units of measurement, and correlation itself has no units.